Okay, welcome back, guys. So now we're going to be covering ANOVA. So we started off with single sample tests where we were kind of comparing a group mean against a hypothesized mean. So we had one group. Then with our auto example in the US and Japan, we were comparing two groups with one another to see if they were the same or if one was greater than the other or one was less than the other, or if they were different than each other. And now we're going to look at ANOVA. And ANOVA is, again, we're comparing means. So we're going to compare means with multiple groups. And with greater or two groups. Now, you can actually do an ANOVA with two groups, but it's the equivalent of doing a two-sample t-test, so it's very rarely done. Generally, if you have like 3 or 4 groups, then you would utilize an ANOVA. So let's think of a very simple example. And imagine we had this scale of fear of statistics. And maybe it's based on the questionnaire I showed you in class of 1 to 100. And this 100 is like very afraid of statistics. So that's kind of this is going to be my dependent variable. Sorry, just squeeze that in there. And my independent variable, or my kind of experimental variable, this is going to be the major. Now, I was going to use some fancy notation. This is just set notation. It says major is one of the following. And let's keep this really simple. So you can be a math major. You can be an English major. You can be a business major. Or you could be an engineering major. And let's give each of these guys a different color. We'll make math black. We'll do English red. We'll do business blue. And we'll do engineering green. So what we're going to do is imagine, let's just draw, we have our scale. Look at that beautiful straight line. And this is going like from 1 to 100. And then we're going to kind of maybe say we had like 20 math majors, 20 English majors, 20 business majors, and 20 engineering majors. So we're gathering samples of each of these majors and then kind of testing whether or not they have a fear of statistics. Sorry, I've got my pen. There we go, engineering majors. So we'll start off with the math. Now, math majors are going to have relatively low fear of statistics. So most of these values are going to be around here. Maybe there's one who's a little bit of a bad math major or just hates stats. So imagine we have like 20 of those. Now the English majors are probably going to have a pretty high fear of statistics. But again, maybe you've got an English major who's also very good at math, so it's not perfect. Business majors, these people range. You've got some who are very mathy, and some, as I've taught business stats before, and you get just basically a whole range of these people. And finally, engineering. It's going to look a little bit more like math, but maybe not quite as much. Now, each of these lines is going to have a mean. It's going to be x bar 4, x bar 3. This one, the mean's probably up here, x bar 2. And the black one is down here, x bar 1. Now, if I was teaching this in a stats class, I would use this to do lots of math and basically all these kind of sum of squares. But we're just going to kind of do it simply conceptually. And let's use rainbow. Maybe we have an overall mean that we're going to call double x bar. And what we're trying to do with ANOVA is basically we want to see the difference between the group means, and we actually conceptualize this as the difference from the overall mean, and we want to do it relative to the variation within the group. So we have the variation between the groups, which is the variation, say, between these kind of 4 group means. You can see x1 bar 1 is down there, x bar 2 is up there, and these guys are in the middle. And then we have the variation within the groups. Which is basically the variance of each group. So that would be the variation within the group. And then the differences between each of these means to the overall mean. This is going to be between the groups. And the idea with ANOVA is we want to show that there's a significant difference between means. So we want the groups to be a long way apart and not much variation within the groups. Because the more variation we have within the groups, the harder to tell that the groups are different. You know, if we have 2 groups like English and business, and they've both got like a load of people at the bottom and they've got a load of people at the top, there might be a slight difference between x bar 2 and x bar 3, but that difference may not be significant. So just like, let's just do a thing, and let's just do 3 groups. So in this little diagram here, the groups are very close together, but there's a big difference between the overall means. So this looks kind of pretty significant. This is going to be kind of significant. But let's look at this scenario where we have the 3 groups and the means are really close to each other and there's a huge variation in each of the groups. Then this is likely to not be significant. And that's essentially what we're testing with ANOVA. If we have these really spread out groups with the means close to each other, it's unlikely we're going to get a significant result, difference between the means. But if we have these kind of tightly packed groups, we're more likely to get a significant result. Okay, so we're going to kind of go back to the slides, and then I'll show you how to implement this in SPSS. Okay, so we're doing ANOVA, and we're doing a very specific ANOVA, which is a one-way ANOVA, which basically means we have one dependent variable, and we have one independent kind of category variable with multiple category levels. If in my business stats, I always kind of covered two-way ANOVA where we had 2 categorical variables, and the book actually mentions n-way ANOVA. But we're just going to kind of keep simple. We're just going to do the very simplest ANOVA because, again, we could spend kind of weeks and weeks on this stuff. I've literally, in my library, I've got a 1,000-page book, and it's just full of all these hundreds of different types of ANOVAs. So we'll do the simple one, which is kind of the one that we use in most kind of marketing research and A/B testing, and we'll just learn that in a little bit of detail. So here's my example. We have, and I'll just show you this, we have 4 different brands of golf ball. So my independent variable is my brand of golf ball. And what we want to know is, does one golf ball brand go further than the other? Which brand goes the furthest? And to do this, we use an ANOVA. So what we're doing here is we're taking samples of basically hitting golf ball A 10 times, hitting 10 golf ball A's, hitting 10 golf ball B's, hitting 10 golf ball C's, and hitting 10 golf ball D's, all done randomly. And this Iron Byron comes in for the fact it's like a mechanical golf machine, which is named after a famous golfer. Okay, so with ANOVA, this is the hypothesis. So where are we? Okay, so the business hypothesis here is the difference traveled by the golf balls, does it differ across the 4 brands tested? Now, really important here, the null hypothesis is just an extension of what we did with the 2 sample. It's is mu1 equal to mu2 equal to mu3 equal to mu4. So i.e. all means are equal. Just a hint, this is the number of kind of category levels in the variable. If we only had like 3 different brands of golf ball, then we wouldn't have mu4. We would get rid of that. We just have mu1, mu2 equals mu2 equals mu3. And that, when I've done exams before, that's actually kind of a common problem in that people look at, my example slides, mu1 equal mu2 equal mu3 equal mu4. But if the exam question only has 3 category levels, then it's only going to be mu1 equals mu2 equals mu3. Now, again, very important. The alternative hypothesis is at least 2 means differ. This is written in terms of this example, but it's at least 2 means differ. What it is not is saying that all the means are different from each other. So it is not this. This would be the wrong answer for an alternative hypothesis on a multiple choice question. Because this is saying all we're checking is we reject the null hypothesis if at least 2 means differ. So mu1 could be the same as mu2, could be the same as mu3, but mu4 could be different from those. And then we would still reject the hypothesis. So this is, just to be 100%, this is wrong. Okay, so this is the test. So we've just kind of covered this. This is just kind of, and I'm not going to go through, again, if I was teaching business stats, I would do a lot of this on ANOVA tables. But the idea is this was called the mean squared treatment, and this is sometimes called the between groups variance. So this is what I showed you visually in the diagram. And on the bottom, we have within groups. So again, that first little example where we have the big difference between the group means and the groups are very tightly packed together, that's going to be, the top one's going to be large and the bottom one's going to be small, giving a big F value. So the bigger the F, the more significant. And as we're not doing all the manual stuff with the ANOVA table for the moment, I will just talk about that when I show you the SPSS output. But this F statistic has degrees of freedom. The top, this is just the number of groups. So in this case, with our golf example, this would be 4 minus 1, which is 3. And at the bottom, we had 40 golf balls hit in total. So that would be 40, and that would be minus 4, which would give 36. But again, we're not focusing in this class in filling in ANOVA tables, though I'm sure you had a lot of fun of it in business stats. And just to remind you, this is what the F looks like. And for any alpha, so again, this type 1 error, which is how strict our test is, so say we said alpha equals 0.05. This is, we're going to reject. So this is my F kind of F star alpha. We're going to reject H0 if F is greater than my F star, my critical value. Okay, so let's actually just draw that again. Make it a little bit bigger. So we have my alpha here, and this is my kind of my critical value of F. Now imagine we have an actual F value. Again, the area to the right is the P value. Sorry, this is the same color. Maybe I should have used the other pad. I prefer them different colors. So this is the P value. No, let's just discard my ink annotations. Let's go back to let's just draw one of these on the whiteboard. Okay, let's just clear that. Okay, so let's draw it in. This is my F. And that's, say, my alpha. And imagine this. So this is my significant F. But this is the F we actually get. And the area to the right is the P value. And again, the P value is just the value's more extreme than your actual test statistic. So we're going to reject H0 if kind of, let's just call it F star alpha. If F is greater than F star alpha, but also in SPSS, we're going to reject if P is less than or equal to alpha. So let's go to my green. So if my F was up here, we're going to reject because my F is bigger than the F star, my critical value, but also my P value is tiny. My P value is less than the alpha value. Okay, so let's do this example in SPSS. But first, let's just talk a little bit about some of the conditions. So we assume that our samples are random from K treatment populations. So imagine we have a populations of A, B, C, and D golf balls. We assume we're randomly selecting 10 golf balls from each. We assume that the sampled populations have approximately normal distributions, but this doesn't matter, again, central limit theorem. This doesn't matter if we have much larger sample sizes. And we assume that the population variances are relatively equal. This isn't that strong. So we will just assume for the moment that generally ANOVA will work when the variances aren't equal. But we'll assume for the moment that the variances are equal. Okay, so let's do this little example in SPSS. So again, we'll see that we have the independent variable in one column, so we have the brand in one column, and we have dependent distances in the second column. So we can see like 10 distances for each of these different brands. Okay, guys, good with that? Okay, and what we're going to do is, and again, as I said before, to get these files, you just kind of do File, Open Data, if you don't already, and you can pick your file, or on a PC, just double click on the file you want. Okay, so let's go and let's go and do kind of the ANOVA. Okay, so we want to go to Analyze, General Linear Model, and Univariate. Okay, so this is actually, we can do lots and lots of different ANOVAs here by all these complicated different types of factors. But I said we're going to keep it simple. Our dependent variable is the distance, and our factor is going to be the brand. Now, we're going to do something I'm going to explain when I show you the results. We're going to add something called a post hoc test. And what we're going to do is we're going to add a post hoc test for the brand. And we're going to do something called a Bonferroni test, which I will explain in a minute. And we're also going to make some plots. And literally, all we're going to do is we're going to plot the brands along the horizontal axis. So we're going to basically have the brands on the horizontal axis, and we're going to plot the values of distance for each. And I'm just going to click Add there. Okay, I think we've finished here, and we're now going to click OK. So again, we're going to have this in the SPS output. Apparently, it's still working. It's happened now. So we got this comes under the univariate analysis of variance. The first table tells us, well, we've got 10 of each type of golf ball. And then we have what's called the ANOVA table. And as I said, if I was teaching this in a stats class, I would actually spend a lot of time talking about, I'd like spend an entire couple of classes talking about ANOVA tables, but we don't have time for this. And then we have the post hoc test. Now what I've done is back in the slides, I've kind of highlighted what you need to know from the ANOVA table. So again, if the P is less than alpha, then we can reject the null hypothesis. There's evidence that the means are not equal, and they're different for at least two of the brands, so we reject the null hypothesis. If the P is greater or equal to alpha, there's not enough evidence, and we fail to reject the null hypothesis. Now be very careful here, because this table can do lots of different, that technique in SPSS can do lots of different things. And basically, this kind of gives the corrected model, if you go back to your business stats, this gives the total sum of squares for your ANOVA table. Then you have the sum of squares for your treatment, which is brand, or your effect, which is brand, and you have the error. I don't expect you to be able to read the ANOVA table for this class, but what you do need to know is for your brand, the significance value. This is your p-value. So this is like really, really significant, this example. So if I was to draw a little f distribution here and say I had my alpha 0.05, what happened there. So say we had the alpha equals 0.05. then that's my my critical F value here. Then my actual F value is way to the right. We're very easily in the critical or the rejection region. Okay, so here we go. P equals 0.000, which is less than 0.05. So we reject H0, and there's evidence that the mean differences for at least the two brands are different. So we reject H0. Now, what's the problem here? Well, I've basically said at least two means are different. So maybe my boss has asked me to, which is the best golf ball brand? And I go back to her and say, well, I don't know, but I know at least two of the means are different. My boss, she's probably going to go, you're a complete idiot. You've not told me anything useful. So that's why we need to do these follow-up or post hoc tests. So yeah, the F test is what's called an omnibus test. It tests that at least something is significant, but it doesn't tell us which group means actually differ from this. And what we're going to do is, the problem is if we do lots of tests of different kind of pairs of means to see if they're different from each other, and each time we have a type 1 error of 0.05, then with lots of tests, we're liable to get a significant result by accident. So what the post hoc test does is it makes my t-test, it makes the comparisons more difficult. And this is quite a complex and detailed area. Now, what we would do is basically we'd do like multiple t-tests. But we make the alpha much smaller. We'd set our new alpha, which we actually call our experimental error rate, which is going to be the old alpha, which is usually 0.05, and we divide it by the number of comparisons. So imagine we had like 3 different brands of golf ball. We could have A and B, A and C, A and D, and we could also have B and C, and we could have B and D, and we could have C and D. We'd have 6. So we have 6 tests, and we divide alpha by the number of tests. But again, this is actually not going to be on the exam, but I wanted to kind of show it you because without post hoc tests, ANOVAs are not that actual useful. So this is the plot that we did before, which we get the results for. And you can see here, and this just basically plots as the average. We're not doing any statistics. It's just plotting as the average distance traveled for each of the golf balls. And we can see, whoa, brand C is definitely the highest, followed by brand B, and brand A and D are pretty much similar. But we look at the post hoc tests, and we actually it actually tells us whether these comparisons are kind of significant. So let's go through this. Brand A minus brand B, the difference is 10. We know A minus B is minus 10, so that means that B is probably bigger than A, and it's going to be significant. So we can actually write this down. So we have B, and it's bigger than A. And C is much bigger than A, and C is much bigger than B. And you can see this is also significant. So C minus B is 0.88 minus 0.8889. So C is 8.989 bigger than B, and this is significant. So we're going to put C up here. And then poor old D. D is actually A minus D is positive. So D is down here. But notice the difference between A and B is greater than alpha, so it's not significant. So we sometimes draw a line to say the difference between the groups is not significant. So we can now say that there's evidence that C goes the highest, B is kind of the next highest, followed by the D and the A. So it kind of fits in with what we think the intuition from the graph. C is significantly the biggest, followed by B, then followed by A and D. But as I've actually put the revision guide up now, I'm not going to cover the post hoc test in the exam because it's a big, I'd spend, if I was teaching this in stats, I'd probably spend kind of a couple of covering this. Okay, so that's all for ANOVA.